Good day, class. So I have decided that I will record everything concerning the psychrometric processes topic so that there will be continuity later on when you listen to the discussion of the solution of the problems that were prepared for such processes. So when we speak of psychrometric processes, these are processes actually that is relying on the use of the psychrometric chart as a source of information for the properties of water vapor and air mixture. Now, when we speak of a sensible cooling process, this is a process wherein the moisture content of air remains constant but its temperature is decreased. How is it decreased? So, air is being passed through over a cooling coil. A cooling coil is simply a coil in which there is a cooling medium that is flowing inside it. Now, for moisture content for this process to remain constant, since the humidity is kept constant in this case, the surface of the cooling coil should be dry and its surface temperature should be greater than the dew point temperature of air. If the cooling coil is 100% effective, your exit temperature for the air as well as with that of the coil should be equal. However, in practice, there's no such process that is 100% efficient or effective, and as such, we expect always that our exit air temperature will be higher than the cooling coil temperature. Now, in a psychrometric chart, the starting point, let's say, is point O, and it will end on a state which is represented here by point A. So, correspondingly, you can read the enthalpies in this manner, so slanted upwards or downwards to the right. This is your humidity here. In some texts, humidity is represented as W. In John Couples and McCabe, I think it's represented as capital letter H to distinguish it from the small letter h, which are used to represent enthalpy. So we know that this is your dry bulb temperature. The horizontal axis value or the ordinates represent the dry bulb temperature. Now, in solving or determining the load that your cooling water should be able to process, and that is, it is able to receive or absorb a certain amount of air so that its temperature is lowered to the desired value, that particular heating load or cooling load in particular is given by this formula. You can work on enthalpies in this side and you can work on temperatures with specific heat in this side. So this is the average specific heat of your air, the CPM. Now, for heating, that's just the opposite of cooling. So in this process, the humidity of air or the moisture content of air remains constant with its temperature being increased. How? So it's passed over a coil in which there is a heating medium inside. So the heat transfer rate during this process is given by the equation that you are seeing here on the left. It's very much similar to what we have under the cooling process. The only difference, of course, is that this one is using an increase in the final temperature, whereas in the cooling process, it's using a value wherein there is an observed decrease in the temperature of the mixture of air and water vapor. Now, the humid specific heat, or we call this just simply the specific heat, the average specific heat of air, and this will be the value that you're going to use, is 1.0216 kilojoule. Take note, per kilogram dry air. So it's accounting for the amount of heat that your 1 kilo of dry air is going to, shall I say, receive or absorb per 1 degree Celsius increase in its temperature. So that's your humid specific heat. Now, heating then is a process that starts from a lesser temperature to higher temperature at constant humidity, and these are your enthalpy values. This is HO and this is HB. Now, if it is cooling with dehumidification, we decrease the temperature of air, at the same time we decrease its moisture content. So when moist air is cooled below its dew point, by bringing it in contact with a cold surface, some of the water vapor that is present on it condenses and leaves the air stream. Now, leaving the air-water vapor mixture with a water vapor content which is lesser than the original. So this will also result both to a temperature and humidity ratio decrease. Now, this process is the normal thing that we have in an air conditioning system. So the reason why that we feel dry if we are exposed to very low air conditioning room or facility is because there is also a decrease in the humidity of air inside that particular room or facility. Although the actual process path will really vary upon the type of the cold surface, the surface temperature, and the flow conditions, for simplicity, the process line will be assumed here to be a straight line. Now, the formula that we will have if we will make a mass balance for water, the total amount of water entering will be represented by this mass of air times the humidity of the air-water vapor mixture. That should be equal to the mass of air and the humidity of the cold air plus the amount of water that was vaporized. So this MW is the amount of water that was class, it's not vaporized, but rather that was condensed because of the cooling process below the dew point temperature of air. Now, if we do energy balance, it's still processed like this. However, we just change the enthalpies here, or rather the humidities that you have, the W's, the two W's here into enthalpy. So you have still original mass of air times its enthalpy plus the load of the cooling coil, plus the energy content of the water that was condensed. So it's mass of water times the enthalpy of this saturated water at the dry bulb temperature indicated at the end of the process, plus this one, the mass of air times its enthalpy at the exit condition that is stated, whether it's in the form of dry bulb temperature or also of humidity, a certain percentage of humidity. Now, in most cases, class, the value of MW, HW product is very small or is non-comparable to these three terms here. So when we just compute for the load of the cooling coil in a cooling and dehumidification process, we simplify it into this form. We take out this MW, HW, the energy content of the condensed water vapor, and we only account for these two so that we can determine the load, the cooling coil load. Now, in here you can see that you have a enthalpies HO and enthalpies HC representing the initial and the final enthalpies of your air-water vapor mixture. Now, it can be observed that the cooling and dehumidification process in this case involves both latent and sensible heat transfer processes. So there is latent heat transfer and there is sensible heat transfer. Hence, the total latent and sensible heat transfer will have an equation that will have all these three present. So this is your total cooling coil load, this is your latent heat transfer, this is your sensible heat transfer. So your Q sub T should be the sum of these two. Now, if you will determine the latent heat, then that would of course be the amount of heat necessary to change the phase of water vapor from gas to liquid. So that could be accomplished by multiplying the mass flow rate of air times the initial enthalpy content minus the enthalpy of the saturated liquid at the final temperature indicated, the dry bulb temperature that is. Another alternative formula that could be used is we will use the lambda, the latent heat of vaporization lambda. So in thermodynamics, your H sub Fg in some other texts is actually equivalent to the difference between the saturated vapor enthalpy and the saturated liquid enthalpy, or this is your lambda for the change from latent heat of vaporization, the change from vapor to liquid. And then we just multiply it with the mass flow rate of air again. By the way, this MA here is mass of dry air times the humidity initial and final. Okay. Now, for the sensible heat, it's the same thing. Mass of dry air times its enthalpy. So you have the enthalpy here, or it could be determined by the MCP delta T formula learned from thermodynamics. So you know already what HW is, the enthalpy of the saturated liquid based on the indicated temperature, and HC is the enthalpy of the mixture, air water vapor mixture at the end of the cooling process. This one is just for the saturated liquid. Where are you going to get this? You can get this from the psychrometric chart, or this can be read from the steam tables. You just base it on the saturated liquid enthalpy based on the temperature. Now, for the CPM MA formula, the delta T, then of course that will use the final temperature minus the initial temperature. So this would be how you're going to determine the latent heat transferred and the sensible heat transferred, the amount of heat that is. Now, when we speak of a cooling and dehumidification process that is normally experienced in an air conditioning system, we have terms like sensible heat factor, bypass factor, and contact factor. So we will go to each one in detail here. So when we speak of the sensible heat factor, it is defined as the ratio of the sensible to total heat transfer. So in normal cases, on 0.75 to 0.8 T value, this is normal for a dry climate like us. A range of value of 0.75 to 0.8 for SHF. A lower value, let's say 0.6, actually is being used in very humid climate like in the part of Saudi Arabia or Oman. Those countries there have this particular SHF for their cooling system or their air conditioning system. Now, if this particular definition here, ratio sensible to total heat transfer rate, translated in the form of a formula, this would be your formula. The sensible heat transferred over the total heat transferred, or the load of your cooling coil. Okay, the ratio, so it's dimensionless. Now, how is this particular cooling with dehumidification process actually happens, or how is it depicted in the form of a schematic diagram? So yeah, let's say you have a cooling coil here. It's expected that in this cooling coil you have cooling medium. As you could see, there is this water here, and this water of course is expected to increase in temperature because it will be subjected to this warm air. So warm air passes through this coil, and in the process a certain amount of energy from this warm air is transferred to your cooling coil, increasing its temperature and resulting to an air-water vapor mixture of lower temperature. Now, you will have the corresponding amount of water here that was condensed in the process. So that's your M sub W, and you have here the final amount of dry air, you have its enthalpy, and you have its humidity here. If it's depicted on your psychrometric chart, this is your initial state and this is your final state. This is your initial humidity, this is your final humidity, this is your initial enthalpy, this is your final enthalpy, and this is just the enthalpy of the saturated water that was condensed. So you drop a vertical line from your starting point and you draw a horizontal line from your final point. Okay, and then the intersection will be the enthalpy of your saturated liquid at this dry bulb temperature. Or as I have said, you can read it from the steam tables using the property of saturated liquid water. Okay, now the bypass factor will use the temperatures only. So you have here the TS, the TC, and the TO. You know already, this is the initial temperature, this is the final dry bulb temperature, and this is your effective surface temperature of the coil, corresponding also to the dew point temperature of your system, your air water vapor system. We call that the effective surface temperature of coil. How is it determined? From the psychrometric chart. You're going to extend this line that connects your initial point to the final point until you reach the 100% saturation line. So you are to connect these three. You extend rather the line connecting point O to point C. The point where it's going to intersect the 100% saturation line will be your effective coil temperature, the T sub S. Okay, and that would be the thing that you're going to substitute here to know the bypass factor. Your contact factor is just your bypass factor subtracted from 1. Now, what's the essence and the significance of the bypass factor? It can be seen here that the higher the bypass factor, the larger will be the difference between the air outlet temperature and the cooling coil temperature, the higher it is. So when your BPF is 1.0, all the air bypasses the coil. It's just like it did not undergo any cooling and dehumidification. And of course, there won't be any decrease in temperature as well as in moisture content. In practice, the bypass factor can be increased by increasing the number of rows in a cooling coil, or by decreasing the air velocity, or by reducing the fin pitch, the distance that is of the fins of your equipment. That facilitates the dehumidification process. Okay, we proceed. Now, for heating and humidification, the opposite of the third process, you heat up and you increase the moisture content. So this is really very practical in countries which experience snow. So during winter, it is essential to heat and humidify the room air for comfort. And this is normally done by first heating the air, sensibly heating it, passing it to a hot coil, and then adding water vapor before it leaves your equipment. So this water vapor is in the form of steam. So there are, as you can see here in the equipment, there are steam nozzles that before the air that was heated exits this particular chamber, it is being sprayed by the steam nozzles. The result is a higher temperature and an increase in humidity. So as you can see, this is your starting point and this is your end point. There's an increase in humidity, and there's also an increase in temperature, and there's also an increase in enthalpy. That's for heating with humidification. So as for the steam rate, how will the shall we say the flow rate of the steam be computed inside the coil? That will be enough to increase the temperature of air, that is the desired exit air temperature. So you have here the mass of dry air, or the mass flow rate of dry air, multiplied to the humidity at the final state and humidity at the initial state. As to the load of the heating coil, or the heat supplied through the heating coil, that way your air increases its heat energy content. That would be just like sensible heating. So you have MA times HD minus HO. This one is very small actually, but most of the time, for accuracy's sake, we account for the amount of water vapor here, the energy content of the water that was added to your air before it exits. So this is mass of water times the enthalpy of water vapor. So this is HW is the enthalpy of the water vapor, or that's your steam, because you're spraying steam on your heated air before it leaves your equipment. So this is your total heating requirement for your heating coil. Now, if there is cooling and dehumidification, there is also cooling with humidification. You cool it, but this time you humidify it. So we just alter a little of what was discussed here in heating and humidification. So we just change it to cooling and humidification. So instead of using steam as water spray for the water that needs to leave, or for your air water vapor mixture that needs to exit your equipment, it would be cold water that you need to spray to it. So you need to cool down its temperature, so it needs to be sprayed with this cold water spray. So during the process, air temperature drops and its humidity increases. This can be achieved by spraying cool water in airstream. The temperature of water should be lower than the dry bulb temperature of air, but higher than its dew point temperature to avoid condensation. So that is, the temperature of the cooling water that is to be used here should be higher than the dew point temperature of air and should be lesser than its initial dry bulb temperature. That way, it will not condense. So this is your process now. There's no need for a cooling coil in this sense because your cooling water sprays already will address the cooling objective, and at the same time it will also address the humidification process. So this is the final representation of the properties of your air: mass of dry air, its temperature, its humidity, and its enthalpy. So in the chart, actually, you can see that this is your initial temperature and this is your final temperature, this one, with this particular humidity value, and this is the dew point temperature. So the dew point temperature plus the dry bulb temperature at the initial condition will enable you to plot this point. Then it will be a as I will say, a constant dew point temperature process here. So this is your dew point temperature. So it will end up here on the final temperature of the cooled humidified air. So this is the final temperature. This is the humidity that you could see. Now, it can be seen that during this process, there is sensible heat transfer from air to water and latent heat transfer from water to air. Hence, the total heat transfer depends upon the water temperature that is used as your cooling sprayed water. If the temperature of the water sprayed is equal to the wet bulb temperature of air, then the net heat transfer will be zero, as the sensible heat transfer from air to water will be equal to latent heat transfer from water to air. If the water temperature is greater than the wet bulb temperature, then there will be a net heat transfer from water to air. If the water temperature is less than the wet bulb temperature, then the net heat transfer will be from air to water. So take note of this very important information. Under a special case, when the spray water is entirely recirculated and is neither being heated nor cooled, meaning it's being used as is where is, the system is perfectly insulated and the makeup water is supplied at wet bulb temperature. Then at steady state, the air undergoes an adiabatic saturation process during which its wet bulb temperature remains constant. This is the process of adiabatic saturation. The air is being saturated to 100% saturation, or depending on the objective of the problem, but its wet bulb temperature is constant, as I have mentioned here. So this is a constant wet bulb temperature process. The process of cooling and humidification is encountered in a wide variety of devices such as evaporative coolers and in the case of cooling towers, or we call it water cooling towers. Now, in the case of heating and dehumidification, so the previous one is heating, is cooling and dehumidification. Rather, it's cooling and humidification. This one is heating and dehumidification. So we increase the temperature, we lower down the moisture content. Now, there is an equivalent of this, but that was heating with humidification. This one, we take out some of the water content of the air-water vapor mixture. How is this accomplished? So this process can be achieved by using a hygroscopic material that you could see here, which absorbs or adsorbs the water vapor from the moisture. If this process is thermally isolated, then the enthalpy of air remains constant. As a result, the temperature of the air increases as its moisture content decreases. This hygroscopic material can be either a solid or a liquid. And in general, in the process of absorption or adsorption of water by this hygroscopic material, it is liberating heat because the process is exothermic. So this is the heat that will heat up your air. So this results in heat that is released during the process, which is absorbed by your water vapor air mixture, resulting to an increase in its enthalpy and its exit temperature. So there will be an increase in the exit temperature. There will also be an increase in the enthalpy of the air-water vapor mixture, while its moisture content is decreased. But we don't say that everything or all the moisture content of your air-water vapor mixture here is being removed. So there's still certain amount of moisture left. So the process is depicted in here. This is your initial state and this is your final state, original and final state. It's a constant wet bulb process. And this is your initial enthalpy, this is your final enthalpy. This is your initial dry bulb temperature. This is your final dry bulb temperature. So the process of heating results in an increase in temperature due to the exothermic nature of the absorption of water. And since there is absorption or adsorption of water, the humidity value is decreased. Now, in mixing of air streams, there are two scenarios: mixing of air streams without condensation and mixing of air streams with condensation. So you have these two air streams here, and this is the resulting mixture of the two air streams. So if you do material balance, then the amount of moisture of the two streams that is initially mixed will result in the total amount of moisture present in the mixture of the two. So this is it. The energy balance is patterned from the mass balance or content in terms of water vapor, and we just change the humidities into enthalpies. So you have already the enthalpies. This is in the case of mixing without condensation. If there is mixing with condensation, as you could see here, now there is a certain amount of water content of these two separate streams that is condensed in the process. So as shown above in the figure, when the very cold and dry air mixes with warm air, and very cold and dry air, so meaning lower temperature, less, very little amount of moisture, is mixed with warm air at high relative humidity. So you mix it with its opposite, high temperature, high relative humidity. The resulting mixture condition may lie in the two-phase region. So this is the two-phase region that is being mentioned. Due to this, the humidity ratio of the resulting mixture, this is 0.3, will be less than that at 0.1 and 2 class. So there's no 0.4 here. So that would be less than that of 0.1 and 2. Of point, in this case, class of 0.2, but greater than that of 0.1. Correspondingly to this, there will be an increase in temperature of air due to the release of latent heat of condensation. So some of the water of the warm air at high relative humidity will expect to be condensed. So in the process of condensation, there will be an increase in the energy content because of the release of this latent heat. This process, however, rarely occurs in an air conditioning system, but this is a phenomenon which results in the formation of fog or frost if the mixture temperature is below 0 degrees Celsius, meaning the temperature here in which the two streams are going to mix is below 0 degrees Celsius. And this is not experienced in our region because this often happens in the western part of the globe. This happens in winter when the cold air near the earth mixes with the humid and warm air, which develops towards the evening or after the rain. Now, so we'll have now sample problems here on the application of the processes I have discussed. I have asked you to read during your dry lab period the 5 sample problems in John Couplis. They are fundamental and they're very easy to follow. I hope you have read those already, because these 3 sample problems will simply complement the problems that I have discussed, that John Couplis already discussed in his book. Now, before we have to start with this particular sample problem, I need to show to you the Cyclomatic chart for this process to be used. So the Cyclomatic chart that we will be using is the one that is present, of course, in your handbook, just as a review. So this is the psychrometric chart that I have shown to you. You need at least two information. You need two information. That way you'll be able to get whatever information that you want to get. So I like to use the 40 degrees Fahrenheit dry bulb temperature and the 36-degree Fahrenheit wet bulb temperature. So if this is 35, this must be 36. We go down until we reach 40. So this is 40. If this is our point 40, this is the point of intersection rather of 36 and 40. This one, you're going to read the other properties of your air water vapor mixture based on this point that I have my cursor on. In this side, you have the enthalpies. In this particular lines, you have the specific volume. So you just approximate where is that line for the specific volume of our mixture here. This is your humidity ratio, or simply the humidity. Okay, now what I'm going to illustrate to you later in the solution are all values already taken from the psychrometric chart. So this is the English psychrometric chart. The units used here are English. The other one that you could see here is SI. So your handbook has both the two units of measurements for you to use, two charts for the different units of measurements to use. So let's go back to our slide. Rather, now let's go to our slide to read the problem, then we'll go to our Jamboard for the solution. So for problem number 1, moist air enters a steam heating coil at 40 degree Fahrenheit and 36 degree Fahrenheit thermodynamic wet bulb temperature, and this is the volumetric flow rate. Now the process is operated at barometric pressure of 14.694 psi air. The air leaves the coil at dry bulb temperature of 140. Determine the pound mass per hour of saturated steam at 220 degrees Fahrenheit that will accomplish the goal of heating up this moist air. And there is this particular information that the condensate leaves the coil at 200 degrees Fahrenheit, meaning a portion of the water vapor in your air is being condensed. So this is a case of heating with dehumidification because part of your water vapor present in the original water vapor air mixture is condensed. Okay, now we'll go to our board and outline the process for this particular sample problem. So I will write down the given information directly. That way we will save time in so this is our problem. Last time I had a problem with my pen. So now we will write here for the solution of sample problem number 1. So in state 1, I'd like to have here state 1. It's still not fixed actually. Your humidity you have 0.00359. So this is equal to, this is your point, 0.00359 with unit pound mass H2O per pound mass dry air. Okay, that's for our humidity. For the enthalpy, we have 13.47. This is BTU per pound mass. Then for the specific volume, so I pointed out already the values where you're going to get this. That's 12.66 cubic feet per pound mass. Okay, so this is for our state 1. So for state 2, this will be your temperature The dry bulb temperature that is to be reached is 140 degrees Fahrenheit. And you have the humidity, .00359. So based on the final temperature, and this is heating, this will be the increased humidity of your air water vapor mixture. So water over pound mass dry air. Okay, and then we have the enthalpy correspondingly equal to 37.70 BTU per pound mass. Okay, now having this particular values, you now go to your solution proper. So these were values taken from the Psychrometric chart. This was the one that I had difficulty last night. Actually, was not able to record last night because I had problem writing on my board, and I think until now I don't know I already changed the tip of the pen, but it's still, I think, pretty much the same. It's still not as the one that I've used before, similar to the one I've used before. Okay, so now we'll have the mass of dry air computed. So this is in initial amount of dry air. Actually, it's the dry air amount is not changed in this process. It's still pretty much the same. So now MA1 will be the volumetric flow rate divided by the specific volume. So volumetric flow rate is a V with this one. Now it's given in the problem that initially you have air in the amount of 2,000 cubic feet per minute. And we divide it by 12.66, one of the values that we got in the psychrometric chart. So cubic feet per pound mass. So you have now the mass flow rate, which is 9,479 pound mass per hour. Okay, by the way, this is the mass flow rate excuse me, of air water vapor mixture. Okay, so this is the mass flow rate of your air water vapor mixture at the start of the process. So state 1, that is. Now if we need to determine the load, the load of the heating coil, that would be the mass flow rate of this air times the change in enthalpy, H2 minus H1. And if we will place in here the value, so the one that we have computed on top, we use, and we multiply it with the enthalpy, which is 37.7, the one that we got from the psychrometric chart. We subtract from it 13.47. Okay, so your resulting value for the heating load is 229.676 BTU per hour. So this is BTU per hour. Now, this Q, as we have discussed, is the total heating load of your coil, and it is the sum of the sensible and the latent heat energies already or transferred. So in this case, that Q will be equated to the Q that we got in the previous slide, will be equated to the MSHG minus plus MSHL. So this is, in some books, your HL is the saturated liquid enthalpy, but in others it's represented as HF, whereas HG is the saturated vapor enthalpy. Now this HG, I'd like to specify, should be at 220 degrees Fahrenheit, and this is for your saturated vapor. This HL should be taken from the steam tables at 200 degrees Fahrenheit, and this is for saturated liquid. If you notice, the difference in these two actually already sums up this is vapor and this is liquid. So if you notice, there is already a change in phase, at the same time a change in temperature. So there is sensible heat and there is latent heat due to the change of phase. That will be all. These two actually, when summed up, in this case you have a difference because there's a change of phase here, will be equated to the amount of the total load that your heating coil should service, or it's its duty to give to the air water vapor mixture. That way will be able to increase the temperature, or rather decrease the temperature of that particular air water vapor mixture. So this is the load of your coil. Now in this case, this one is the energy content, of your water vapor, that is. This one is subtracted because some of the water vapor present in your air water vapor mixture was condensed and separated from the mixture, resulting to a heated water air vapor mixture, but this time a decrease in its humidity value because some of the water that it originally contains was already separated from it. So you're going to get the values of the HG and the HL from the steam tables. Okay, so from the steam tables, this will be the value of 2. You have for HG, and for HL, saturated liquid, this is saturated liquid, you have 108.34. Now if you will substitute the two, you will be able to get the amount of steam that will be used in this process. So based on that particular formula, we have written your Q is equal to MS, you have HG minus HL. Latent heat, the latent heat of vaporization of your steam will be the one that will heat up your air water vapor mixture. So you will have M, this is the M that we want, This is, by the way, the M that is represented in the slide as to the heating coil load for this particular problem. So you have your Q to be 229. Here we go again. So we have 229.676. That's for the Q. We divide it with the difference of these two. So for HG, you have 1153.28. And for HL, you have 1. I cannot understand my handwriting. 168.34. Let me check if it's the same thing that I have written on the other slide. Oh. 108. Okay. Then we'll have it as 108 here for consistency. Kindly check, class, whether when you do your computation, this would be really 168 or 108. I don't have here a table right now which could check the actual value. I cannot understand my handwriting. It's either a 0 or a 8 in here. But in that case, you will have a final value for M, which is 232.5 pound mass per hour. So this is the amount, this is the flow rate of the steam that will be able to supply the heating requirement for your air water vapor mixture. So a part of that steam, since it's going to liberate its energy content, will be condensed. As you can see here, there's a condensed part here, and this is your liquid and this is your vapor. So there's a change in phase for your steam. So this is the energy content of that particular steam, or the same energy content that your air water vapor mixture is going to receive. Okay, so we go back to our sample problem number 2. The first one is heating, and we have this one now. Moist air enters a cooling coil at 28 degrees Celsius, dry bulb temperature, and 50% relative humidity. So you're going to use this value, the 50% relative humidity and the 28 degrees Celsius dBT, to find the characteristics of your air water vapor mixture at this initial condition. The mass flow rate is given as 1.5 kilograms per second. Barometric pressure is at standard 101.325 kilopascal. The air lives at 13 degrees Celsius dry bulb temperature and 90% relative humidity. Calculate the air conditioning load on the coil, and using the bypass factor approach, determine the sensible heat, the latent heat, the total loads on the coil, the apparatus dew point temperature, and the bypass factor if your sensible heat factor is 0.63. So meaning for this last statement here, you're going to determine all of this if the sensible heating factor is equal to 0.63. So this is our sample problem number 2. So let's go to our board. The sample problem number 2. So our given is for state 1, the original state, that is properties. You have humidity equal to 0.0118. So kilogram water per kilogram dry air. Then you have H1, its enthalpy, this is humidity. You have 58.2 kilojoule per kilogram. Okay, so for state 2, we have this humidity 0.084. I will not anymore write the units, anyway you know the units here. You have your enthalpy. Oh my, okay class. You have H2, the enthalpy 34.2. And you have here, you can get from the steam table the saturated liquid enthalpy. This is from steam saturated liquid. This is to be taken from the steam tables. Based on the state 2 dry bulb temperature, and the value, oh sorry class, and the value of this is equal to 53.61. Now going to do the solution for this problem. So you have cooling in this case, so you have Q being equal to the mass flow rate of air times the change in enthalpy, state 2, state 1, and this time we will consider the condensate. So the condensate is, of course, we'll be using the humidities. This is mass of dry air only, and you have HL2, its enthalpy. This one is for the condensate. This can be actually assumed to be negligible in value compared to this, and you can take it out of the picture, but putting it there will make your solution more accurate. So it doesn't really matter if you take it out, but it's better that it's written or counted for in there. So if you will use the values that we have now, your Q is equal to 1.5. We multiply it to the enthalpies that was presented to you in the previous sheet. So you have 34.2 minus 58.2. Okay, minus, this time we have the humidities. So there are times that I'm saying that it's enthalpy, but remember class, it's humidity. Sometimes I easily blurt out things and then I recall what did I say. Okay, so you have 0.0118 and you multiply it with the saturated liquid enthalpy based on the exit dry bulb temperature for air. So 53.61. Okay, so you'll be computing here a value of negative 35.7 kilojoule per second. Okay, this is for the Q. So your water, your water vapor air mixture in this case. So let's go back. So why is it negative in the first place? So you can see that your moist air enters a cooling coil. So it will be cooled, and as such, your air water vapor mixture is going to release and amount of energy that will enable it to decrease its temperature, or that will enable it to cool down. So that explains the Q, which is negative 35.7. So this is your Q if you consider the condensate. Now you can redo as an exercise this particular sample problem without having to consider this condensate. So if you will redo it, if there's no condensate, okay, here we go again. Your Q without condensate will be 36. It will be 36. So a difference of 0.03, negative 36 kilojoule per second. So if you could see, the value is really not that significant, the value of if we accounted for the condensate. Okay, now we will use the sensitive heating factor that was mentioned in the problem to determine the required information. So by the way, the problem requires us to, let's go back, calculate the air conditioning load on the coil, and we just did that. So that's the Q. Calculate the air conditioning load on the coil, the load that your coil will have to perform, that is. Next will be using this sensitive heating factor of 0.63. You are to determine the bypass factor, the sensible heat, the latent heat, and the total loads of the coil, and the apparatus dew point temperature, if we will use this particular sensible heat factor of 0.63. So your sensible heat factor is equal to 0.63, and this is equal to sensible heat over sensible heat plus latent heat. Okay, now we will determine the latent heat here. So everything is to be substituted. So you have the QS already accounted for, and that's the, and by the way, we don't know yet the QS, so we need to determine first the QS. So let me first start with, we'll just have that as our equation 1. We need first to determine the QS because it's not known there. If it's known, then we can determine the latent heat. So we'll have this as equation 1. Okay, now we can determine the dew point temperature. So in determining the dew point temperature, and that would be your effective coil temperature. So I have mentioned during the discussion that the dew point temperature is your effective coil temperature also. How will you find it? From the Psychrometric chart, you can read this one more or less to be equal to 10.3 degrees Celsius. So from the line connecting your initial condition, so I don't want to go to the psychrometric chart anymore. You have anyways the dry bulb temperature and the wet and the relative humidity value. So you have that value to use, the pair, the dry bulb temperature and relative humidity percent. That would lead to you the initial point, and then you have also another two sets of values that will lead to the final point. What you do, the line connecting these 2 points, you will extend until it will reach the 100% saturation line. When it reaches the 100% saturation line, you read that particular, from that particular point, which is the extension of the lines connecting state 1 and 2 on the 100% relative humidity saturated line, you will read the dew point temperature of 10.3 degrees Celsius. So you're going to read the dew point temperature horizontally. So we have discussed that in the first set of slides last meeting. Reading the dew point temperature is horizontal. So you just locate for that extended point on your 100% saturation line and read the dew point temperature horizontally. So the value that you will be getting more or less is 10.3 degrees Celsius. Now you use that value in determining the bypass factor. So we can actually determine first the bypass factor. So your bypass factor is based on the formula, which is actually TO, T initial, minus TS over T final, minus TS. So in this case, you have a 13 minus 10.3 over 28 minus 10.3. Okay, so giving you a bypass factor of 0.153. Okay, that's your bypass factor. We have answered that already. I'd like to go back to our problem and let me check about the temperature. So 28, and then it will leave at 13. So this is cooling with condensation. Okay. And air leaves at 13. So based on the formula that I have written, leaves at 13. So the 13 class, by the way, is not the initial temperature, but rather the final temperature, because we have a case of cooling. So I will just change this one. So this is final state, this is initial state. Okay? That would be 13 for the final, and you have 28 for the initial, giving you this bypass factor. So we have already answered the bypass factor. I can only determine the latent heat here if I already know the sensible heat. So we first determine the sensible heat. Your sensible heat can be used using the thermodynamic basic principle of MCP delta T. So in this case, we will use the mass of dry air, its humid heat, or the average specific heat, times its temperature, T1 minus T final, and we have 1 minus the bypass factor. So the purpose of determining the bypass factor is for us to be able to multiply the sensible heat formula, class O, due to the change in temperature, by the contact factor. The difference of one of the bypass factor, if it's from 1, that is. So 1 minus the bypass factor is your contact factor. So you have to multiply the original MCP delta T from your thermodynamics, in this case, by the, I'd like to place here as a correction, the contact, I don't know why this is happening, the contact factor. That would be, you're going to multiply this by the contact factor. This is in this case of cooling with condensation. So contact factor. Okay. Now the contact factor is this one as discussed. So you, there's something wrong with this one. So you need to now substitute the value. So your M is 1.5. That's the mass flow rate. And then your humid heat was given to you already at 1.02. Then your T1 is 28. Your T2 is 10.3. And you have 1 minus the computed bypass factor, which is your contact factor. So take note of this. Accounting for sensible heat in the case of cooling with condensation or cooling with dehumidification has this correction factor, the contact factor in the standard fundamental formula for sensible heat transfer from thermodynamics. So you have now the value being equal to 22.9. 22.9, so this would be kilojoule per second. Okay, kilojoule per second. Nice, sensible heat that is. Now we go to the use of the formula that we have to get the latent heat. So from our equation 1 in the last two slides, in the previous two slides, you have 0.63 being equal to the one that we just solved, the 22.9. So you have 22.9 plus the latent heat transfer. So in this case, you will have a value which is 13.4. Now, if this 13.4, if we use remember we use the bypass factor formula and the sensible heat factor. If this 13.4, if we will account for the total cooling load of your coil, that would be 13.4, the latent heat, plus the sensible heat, which is 22.9. This will result to 36.3 kilojoule per second. So in that case, it's not far from the value that we have here in the original Q, which is 35.7. This one is 36.3. If we use a different route in the solution, if we use the sensitive heating factor that was given to us. So your Q actually is negative 35.7. It's negative 36 if we did not consider the condensate. If we did not consider the condensate, our answer will be, the negative 36 will be closer to the one that we have here, which is 36.3. Okay, but this is just a scenario that is given in the problem, comparing methods. That is, the one is using the pure energy balance and this one is using the bypass factor formula with the use of the given sensitive heating factor. Okay, so that ends our sample problem number 2. We have determined the total load, cooling load, based on the sensitive heating factor and the bypass factor formulas. Now, and by the way, the dew point temperature that was asked in the problem, I'd like to go back to that. So we have answered the bypass factor, the sensible heat, the latent heat, the total load on the coil, and the apparatus dew point temperature. I have mentioned that in here, that your apparatus dew point temperature is the effective coil temperature. Your apparatus dew point temperature is your effective coil temperature, T sub S as well. And I have already discussed how you're going to get or read from the psychrometric chart the value of 10.3. Okay, so we are now on the last sample problem. And this one entails mixing. So sample problem number 3. So for this sample problem number 3, this would be the values you're going to read from the psychrometric chart. In state 1, you have the humid volume or the specific volume. So 13.28 cubic feet per minute. And you have the humidity, which is 0.00867 pound per pound mass. In state 2, rather, this is not state 2. Since we have the mixing, we will solve the problem later. So we have here stream 1 and we have stream 2. So for stream 2, this is your specific volume. And your humidity. Oh, sorry. Your humidity. Pound mass water per pound mass dry air. Now, these are the values for stream 1 and stream 2 that you can get based on the condition for this stream stated in sample problem number 3. So, we will read that sample problem. That way, you will be able to connect the values that I have placed in there in our Jamboard. So, for this particular sample problem, one stream of moist air flowing at 1,000 cubic feet per minute at 60 degrees Fahrenheit dry bulb and 56 degree Fahrenheit wet bulb is mixed with the second stream 400 cubic feet per minute 80 degrees dry bulb. This is Fahrenheit, by the way, class, and 67 degrees Fahrenheit wet bulb temperature. So barometric condition is pretty much the same. The standard, that is, determine the dry bulb and the wet bulb temperature of the resulting stream. You are also to calculate the volumetric flow rate of the standard air of the moist air stream at state 1. Calculate the volumetric flow rate of the standard air of the moist air stream at state 1 in the case in here. Okay, now we will go now to our board. Okay, so these are our information taken from the psychrometric chart based on the conditions that were stated. That I will leave to you as an exercise how you will get these two values based on the conditions stated in the problem. We are to solve for the mass flow rate of stream 1, air flow rate, that is. So you have its volumetric flow rate of 1,000. We divide it by this one, the specific volume, the 13.28. This is 28. So this will give you a value of 75.3. This is pound mass per minute. For stream 2, the same thing. So you use the volumetric flow rate that is stated, which is 400, and you divide that by the volumetric, or rather by the specific volume. So you will have here a value which is 28.9 pound mass per minute. So the total mass, that is, of the mixed stream will be the sum of the two, the 75.3 and the 28.9, giving you 104.2. Okay, also having unit pound mass per minute. Now, if you're going to do energy balance, using energy balance, then it would be better if we start, no, not energy balance, by the way, we will use water balance. So, water balance. If you're going to use water balance, we need to account for the total water coming in. So, that would be humidity, or the total water resulting from the mixture of streams 1 and 2. So, humidity of the mixture times its, I have a problem with my cursor, with my pen, times its mass flow rate. Here we go again, and that would be equated to humidity of the second stream times its mass flow rate plus humidity of the first stream times its mass flow rate. That's it. Water balance. So these are amounts of air, dry air, Ma3, Ma2, Ma1. If you multiply it with the humidities, then you will be getting the amount of water present in each of these terms here. So I'll just continue on the next slide. Your H3 then would be equal to your 28.9 over 104.2, this is the total, by the way, times 0.013 only. One, 2, 3, and we have 75.3 over 104.2. So each of the mass flow rates were divided by the total already. So you will multiply this with its for stream 1, 0.00867. So this is actually Ma2H2, Ma1H1. We just divided it by the Ma3 to get H3 coming from the formula that we have here, so that we will know the humidity H3 of our resulting mixture. Okay, so if you're going to do that, you do the math. Your H3 here will have a value of 0.00938 pound mass H2O pound mass dry air. Okay, that would be for our H3. Now, finding the temperature, the dry bulb temperature, could be as easy as you plot the stream 1 location, then you plot the stream 2 location, you connect the two streams. Now, somewhere in between will be your stream 3. It's like right in here. So, in your psychrometric chart, if this is your stream 1, oh my, what's the matter with this? If this is your stream 1 location and this is your stream 2 location, you connect the two. So you know how to find these two anyway. You have the state, the initial state, or you can use the humidity that you have and the dry bulb temperature. So you have here dBT, and you have here your humidity H, or it could be W. So using any of the two values or the conditions that's stated in the problem, you'll have this 2. Now, since you already solved for the H3, that H3 you find here. And then you project it here. Now, you read the dry bulb temperature here. So, this will be the dry bulb temperature T sub 3. This will correspond to a value which is 65.5, more or less 65.5 degrees Fahrenheit. As for the dew point temperature, that would be the dew point temperature that you're going to read here, because we're reading the dew point temperature horizontally, and there's another line here in your psychrometric chart for that. If I'm not mistaken, actually the dew point temperature is before the reading for the humidity. That's how simple it is. You connect the two, you solve for H3. This is H3 value, and then you have the T3 read from the psychrometric chart. If you want it solved analytically, it can be patterned after the water balance that we did, the water balance equation, this one. So instead of having here humidities, you can place here temperatures, dry bulb temperature. If you do that, so you have an alternative way of finding T3. So T3 can actually be 75.3. This is 104.2. If I'm not mistaken, this is for your stream 1. Okay, your 75.2 or 75.3. Wait, class, where did I get the 75.3? This one, the mass flow rate for stream 1, here, 75.3. And then we divide it by the total that you could see here, which is 104.2. You do the same for stream 2, 400 divided by this one. So this is the one that we're using here, and here, to get the enthalpy of the, rather the humidity. It's this the humidity of your resulting mixture. So you can use the same principle in here in finding the dry bulb temperature of the resulting mixture. So you have 60 here for stream 1 for the dry bulb temperature, and for stream 2 you have this mass flow rate. We divide it by the total mass flow rate and the dry bulb temperature, which is 80 for stream 2. Your T3 here computed would also be around 65.5. So you can read it from the chart or you can solve it analytically. Either which, more or less, your value will really not differ that much. So what you have here are simple illustrations or problems using the principles discussed of mixing, cooling, and dehumidification, and heating. So you go over again the solution, you go over again this recorded discussion, and should you have any question, feel free to write me in Canvas to inbox or even to the discussion video link that I will post below. You can post your queries. Okay, so hopefully everything had been made clear, class.